Welcome back to the show, everyone. Today, we're going to be taking a deep dive into a paper that uses quantum harmonic analysis to reprove the Berger Coburn theorem.
Yeah.
Now, I know this audience doesn't really need a refresher on advanced mathematics,
Right.
but this approach is really elegant, and I'm really excited to unpack it with you.
Yeah, it's fascinating how this paper leverages quantum harmonic analysis, or QHA as we'll call it sometimes, to streamline the proof and just offer some really fresh perspectives, I think, on the Berger Coburn theorem.
Yeah, before we get into the specifics of QHA, can we just briefly revisit like the core concepts at play here? The Bargmann-Fock space, Toeplitz operators,
Yeah.
and then the Berger Coburn theorem itself.
Of course. So the Bargmann-Fock space is denoted as 2 pi n. It consists of entire functions on MathBBZ that are square integrable with respect to the Gaussian measure GDC, where DVC is the Lebesgue measure on MathBBZ.
Okay.
And then Toeplitz operators are denoted with 2 pas, and they're defined on Toeplitz using a symbol function, which we just call. And they act by first multiplying a function by the symbol and then projecting the result back into FBC and MathBT.
Gotcha. So the Berger Coburn theorem attempts to characterize the boundedness of these Toeplitz operators.
Exactly. It links the boundedness of T-dolls to the boundedness of the heat flow of the symbol A, which is also known as the t-Berezin transform. And we denote that by BA.
Okay.
And the theorem states that if T-doll is bounded, then B-days is bounded for all T-dolls to 2. Conversely, if B-doll is bounded for some 0 T-doll 2, then T-dollars is bounded.
That T-days 12-2 case still remains an open question, right?
Yeah, it does.
Kind of a head scratcher. Now, how does quantum harmonic analysis simplify this whole picture?
So QHA provides a framework where we can express these concepts, particularly Toeplitz operators and the Berezin transform as convolutions.
Okay.
And this allows us to leverage the powerful machinery of convolution inequalities and the operator heat semigroup to streamline the proof.
Can you just elaborate on the key elements of QHA that we'll need to understand this approach?
Certainly. First, we have the QHA translation of an operator.
Okay.
So for an operator on E, say, T $, its translation by CS in MathBBC is given by LWS T SDBC, where wall are the Weyl unitary operators defined by LECSE EZ22 WC.
So we're essentially just shifting the operator around our space using these Weyl operators.
Yes, exactly.
Interesting. What about convolution in the QHA setting?
So we have 2 types of convolutions. We have one between a function and an operator, and then another between 2 operators.
Oh.
So the convolution of a function and an operator is given by SCSD SUDC, provided the integral makes sense.
Okay.
Similarly, for 2 operators AST, their convolution is defined as ECZ if SECT is trace class for all DBCSTs.
Gotcha. These convolutions seem to be pretty central to the whole QHA approach. Are there any important inequalities related to them?
Yeah, we have QHA Young's inequalities. For instance, if psi and LP, Nis and LP, is in the Schatten class mathcall F2, then psi and mathcall F2 amp2 with frat1 place fat1 plu and A place F prag mu.
Okay.
Similar inequalities hold for convolutions between operators in appropriate Schatten classes.
So these inequalities provide a way to control the Schatten norm of the convolution based on the norms of the individual components.
Exactly.
That'll probably be pretty helpful in analyzing the boundedness of the Toeplitz operators. But how do Toeplitz operators themselves fit into this convolution framework?
Well, one of the key insights of this paper is representing Toeplitz operators as convolutions.
Okay.
So the projection operator onto Taffin math theorem can be written as math Meikle DSDZ, math BEZ, where Canfidoller is the normalized reproducing kernel at psi Raymer. Then the Toeplitz operator, Telgol, can be expressed as a convolution. Tel of phi for in L2 bill.
That's pretty clever.
Yeah.
And I'm guessing the Berezin transform also has a convolution representation in this framework?
Absolutely. The Berezin transform for functions is given by BF is SEZ22 is the normalized Gaussian. It can be shown that Berezin FTZ oval 622 is the normalized Gaussian. And we can extend this to operators.
Okay.
The Berezin transform of an operator dollar is given by BSE CCC wrangle, and it turns out that BAC equals SE.
So both Toeplitz operators and the Berezin transform can be really elegantly expressed as convolutions within this QHA framework.
Exactly.
This is starting to paint a clearer picture of how QHA simplifies the analysis. Now, the paper also mentions the operator heat semigroup. What role does that play?
So the operator heat semigroup is denoted fit for $2, and it's a family of operators on $2 $3 that satisfies the heat equation. Fet Bessie Ophi or like C is a certain differential operator,
Right.
and it acts like a smoothing operator, much like the heat kernel for functions.
Right. I'm familiar with the heat kernel and its smoothing properties for functions, so it seems like this operator heat semigroup is playing an analogous role, but for operators...
Precisely. In fact, fit roles can be written explicitly as sum fit, 2 meters plus nt, where m dollars are certain projection operators related to the eigenspaces of Lawler.
Okay.
This expression shows that fit role is trace class for $2. Interestingly, we can even extend this definition to $2 full of $12, and in this range, fit lore remains trace class.
Extending the definition to negative time values seems a little bit counterintuitive at first.
It does.
I'm curious to see how that plays out in this proof. The paper also mentions densely defined operators. Can you explain what those are and how QHA helps us handle them?
Sure. So densely defined operators are operators that might not be defined on the entire Bargmann-Fock space, but are well defined on a dense subspace.
Okay.
Toeplitz operators with unbounded symbols are prime examples.
Gotcha.
And the paper focuses on the subspace spanned by the normalized reproducing kernels, which is dense in path teen.
So we're essentially working on like a good subset where these operators behave nicely. And since this subset is dense, we can extend our results to the entire space. But how do we define convolutions for these densely defined operators?
So for a function in BC and a densely defined operator self-size exists, if for any indels in our dense subspace and any indels in F2 arg S F2 for some constant dollar, if this condition holds, then ambiguity is defined as before.
Okay, it seems like this condition is ensuring that the convolution integral doesn't blow up.
Yes.
And remains well-defined. Are there any specific examples where this comes into play?
Yes. A crucial example is the Toeplitz operator. For a symbol $A belonging to a certain symbol class, A 2000 lambda, which we'll discuss shortly, a phi exists as a densely defined operator on the span of $, and moreover, it equals the Toeplitz operator T$ on this dense subspace.
So even for these potentially unbounded symbols, we can still represent the Toeplitz operator as a convolution.
Exactly.
That's pretty powerful.
Yeah.
Can you tell us more about this symbol class, A2 lambda?
So the symbol class consists of functions that, while potentially unbounded, don't grow too rapidly.
Okay.
Specifically, a name and norma, if for any norma the mass dou loss plus ZU belongs to L2, and its tall toe to norm is bounded by a constant times E lambda.
So it's a way of like controlling the growth of these symbols as we shift them around.
Yes.
I'm starting to see how this could be relevant for studying densely defined Toeplitz operators.
Exactly. And a key property of these A22 functions is that when you convolve them with the heat kernel finish, the result stays within the same class.
Okay.
Moreover, the convolutions with petite a fit and finis a fit.
So even as these symbols are kind of evolving over time due to the heat flow,
Right.
they retain this crucial property of belonging to A22 lambda. That seems important.
It is, and there's another interesting property. If for some teledome belongs to some L-T space, then for all tutela a fit will also belong to that L-theta space. So this gives us some control over the long-term behavior of the convolutions.
This is already giving me a much clearer picture of how QHA is providing the right tools to approach this Berger Coburn theorem.
Yeah.
We have these densely defined Toeplitz operators with symbols in this special class A2 lambda.
Right.
And we can express them and the Berezin transform as convolutions.
Exactly.
And on top of that, we have these convolution inequalities and the operator heat semigroup at our disposal.
You're absolutely right. And with all these pieces in place, we're ready to delve into the simplified proof of the Berger Coburn theorem.
Before we jump into the proof itself, I'd like to just solidify our understanding of convolutions between densely defined operators.
Sure.
Could you quickly walk us through that definition again?
Of course. For densely defined operators, di-Sobralers, we define their convolution as ZST, provided that SLZ is a trace class operator for all Zeilers in Math BBC.
Right. That trace class condition is crucial for ensuring that the convolution is well defined. Now, we already know that the Berezin transform can be expressed as a convolution with fire.
Yes.
Does this hold even for densely defined operators?
Yes, it does. Even for a densely defined operators, 1 of BSS equals S phi.
Okay.
And importantly, the Berezin transform remains injective even in this setting.
Okay.
This means if two densely defined operators have the same Berezin transform, they must be the same operator.
That's a powerful tool for proving operator equality.
It is.
So we have all the ingredients.
Right.
Densely defined operators, their convolutions, the injectivity of the Berezin transform, and this framework of QHA.
Now let's finally dive into the proof of the Berger Coburn theorem.
Yeah, let's take a moment to appreciate the elegance of this setup.
Yeah.
By representing Toeplitz operators and the Berezin transform as convolutions, QHA provides a direct path to understanding the connection between the boundedness of the operator and the behavior of the heat flow of its symbol. It's like QHA is giving us a new language to express these concepts in a way that makes the underlying relationships much clearer. I'm eager to see how this plays out in the proof. Shall we continue?
Let's do it. Okay, so let's begin with the first part of the Berger Coburn theorem. If the Toeplitz operator t $$ is bounded, then its t-Berezin transform to t is bounded for all t of $2.
Okay.
The key to proving this using QHA lies in the following identity. For 10, 12, 2 I in A2 lambda such that t$ is bounded, we have all t$ t around.
So we're directly linking the heat flow of the symbol to the Toeplitz operator itself.
Exactly.
Through convolution with the operator heat semigroup, how does this identity help us prove the boundedness of d$?
So remember the QHA-Young's inequality.
Yeah.
Since t$ is bounded, it belongs to the Schatten class in $50, and we know 51 is trace class for t$ too.
Right.
Therefore, their convolution BT is also in Math K Tower, which means it's a bounded operator.
Okay.
Moreover, we can bound its norm. We get quad dt d n1.
So we've bounded the norm of the t-Berezin transform by the norm of the Toeplitz operator and the trace norm of 51. Can we say anything more explicit about that trace norm?
Absolutely. We have an explicit formula for the trace norm of 50 for TT1.
Okay.
For TC1, we have 1E2 no. And for 12BTO, we have 9T1.
Okay.
In our case, since 212.2, we use the first formula with TD1 to get PT1 and TT1 to T11.
Okay, so putting it all together would have a concrete bound on the norm of the t-Berezin transform.
Right.
This really beautifully demonstrates how QHA, with its convolution representations and inequalities, provides a direct path to proving this first part of the Berger Coburn theorem.
It is quite elegant.
Yeah.
Now let's move on to the second part of the theorem.
Okay.
If PT2 is bounded for some $0 212.2, then θ is bounded. Here the key is to consider the convolution of BA Tayway fused with BA with football.
I'm seeing where this is going since $0,
Yeah.
12 to 2, we have $12 in DA dollar, which means VD is well defined in trace class.
Right.
But how does this convolution relate to the Toeplitz operator t-ball?
So the crucial observation here is that this convolution is equal to the Toeplitz operator $2,
Okay.
at least on the dense subspace spanned by the reproducing kernels.
Uh-huh.
This might not hold on the entire Bargmann-Fock space because $2 could be densely defined.
Right.
However, this equality on the dense subspace, combined with the injectivity of the Berezin transform, allows us to conclude that BATA operators.
It's a clever use of the Berezin transform's injectivity. We're essentially using it as like a fingerprint to match these operators.
Yeah, exactly.
But how do we actually show that the convolution and t-dollars have the same Berezin transform?
So it boils down to the properties of convolutions and the Berezin transform. Using the fact that the Berezin transform can be expressed as convolution with phi, we can show that BTA. Now, using the properties of the operator heat semigroup, we have phi1TA.
Oh.
Further, since $0 we have $12 1T 1 day, and we can apply the identity we established earlier to get B1T TA1T phi.
Yeah.
Putting it all together, we have BTA, BA1.
Yeah.
That's a really neat chain of equalities. So we've shown that the Berezin transform of the convolution PTA is the same as the Berezin transform of T1T. And since the Berezin transform is injective, this implies that BTA phi, at least on the dense subspace.
Exactly.
And now that we have this equality, we can use the properties of convolutions and the operator heat semigroup to show that $t is bounded.
Right.
We know that BDA is bounded by assumption and the PAD is trace class because light RTT$. Can we use this information to bound the norm of T-day? Yes, we can. Applying the QHA-Young's inequality, we get Lexi and Young-Lex Lex 8T lum.
Okay.
And using the explicit formula for the trace norm of Weffuler for 1E2 all dollars, we get Lexi 1 2 letters 1 1 $2. We get Lempute 1 Telthy and 1 2 day.
Okay.
Therefore, we have a concrete bound on the norm of the Toeplitz operator.
Right.
So we've not only proven that Toeplitz bounded if BIST is bounded for some 0 to 12, but we've also obtained like an explicit bound on its norm.
We have.
And all of this just by weaving together the power of QHA, the properties of convolutions, and the operator heat semigroup.
It's a beautiful testament to the clarifying power of QHA in this context. By viewing these operators and transforms through the lens of convolutions, we can uncover these deep connections and streamline the proofs in a very satisfying way. I'm thoroughly impressed by just the elegance and efficiency of this whole QHA-based approach.
Right.
It's given me a whole new appreciation for the depth and interconnectedness of all these concepts.
And there's still more to explore, right? The paper also delves into the application of QHA to understanding Schatten class membership and compactness of densely defined Toeplitz operators.
You're exactly right. The insights we've gained so far extend beautifully to these other important properties. But perhaps we should pause here for a moment.
Yes,
Let these results sink in before we continue our exploration.
I agree.
We'll be back soon to delve into those fascinating results on Schatten classes and compactness. Stay tuned. Welcome back. We've seen how quantum harmonic analysis provides a really powerful framework for understanding the Berger-Coburn theorem. Now let's explore how QHA sheds light on Schatten class membership and compactness of densely defined Toeplitz operators.
Yeah, so Schatten classes are denoted math chemical, and they classify compact operators based on the decay rate of their singular values.
Wow.
The smaller the value of the faster the decay, and in a sense, the nicer the operator is.
So it's like a hierarchy of well-behaved compact operators. How does the Berger-Coburn theorem viewed through the lens of QHA connect to these Schatten classes?
Okay, so the paper presents a quantitative version of the theorem for Schatten class membership. It states that if a densely defined Toeplitz operator TA belongs to the Schatten class mathcalis PF2 for $1 8PFD, then the t-Berezin transform of its symbol BTA must belong to the function space LP at FDU for all T12 2FR.
So the Schatten class of the operator is reflected in the function space of its symbol's heat flow.
Yes.
And you mentioned a quantitative version. What kind of explicit bounds do we get?
The paper shows that for TAT1, we have 2T1, TS.
Wow.
This inequality provides a precise relationship between the LPAL norm of the t-Berezin transform and the mathcal norm of the Toeplitz operator.
That's a remarkably concrete connection. What about the converse? If we know that t-Berezin belongs to ELP for some $0.12.2, can we say anything about the Schatten class membership of T2?
Yes, we can. The paper establishes that in this case, $2 must belong to math2nax, and we have the bound to PFE2. So we have this beautiful two-way relationship. The Schatten class membership of the operator is directly tied to the function space membership of its symbol's heat flow.
Right.
And QHA provides the tools to make this connection explicit.
It's quite striking how QHA unveils these relationships. Now let's turn our attention to compactness. Recall that compact operators, in a sense, smooth out the functions they act on, making them more well-behaved.
Right, and compactness is a desirable property for operators, leading to many useful results. How does QHA help us characterize the compactness of these densely defined Toeplitz operators?
Well, the paper states that a densely defined Toeplitz operator, TFTA, belongs to the space of continuous functions that vanish at infinity, denoted TC dueller TT, belong to the space of continuous functions that vanish at infinity, denoted C duellers, for all T22.
So the compactness of the operator is captured by the long-term behavior of the symbol's heat flow.
It has to fade away as we move far from the origin.
Precisely, and the converse also holds if BTA belongs to C dollars for some $0.12.2, then the Toeplitz operator 2 tal a day is compact.
Once again, QHA gives us this elegant equivalence between a property of the operator and a property of its symbol's heat flow.
It's remarkable how QHA simplifies these characterizations. By viewing Toeplitz operators and the Berezin transform through the lens of convolutions, and by utilizing the properties of the operator heat semigroup, we can directly link the compactness and Schatten class membership of the operator to the behavior of its symbol's heat flow.
This has been an incredibly illuminating deep dive. The power and elegance of the QHA approach are truly impressive. It's given me a whole new appreciation for the depth and interconnectedness of all these concepts.
And it leaves us with some intriguing open questions to ponder.
Right.
Remember the open question about the cello 12-2 case in the Berger-Coburn theorem? Perhaps QHA could provide the tools to tackle that puzzle. Could it help us determine whether the boundedness of B12s is sufficient to guarantee the boundedness of the Toeplitz operator?
That's a fantastic question. It really underscores the potential of QHA to push the boundaries of our understanding in this area. It's been a pleasure exploring these ideas with you.
The pleasure was all mine. It's always exciting to delve into the elegant world of QHA and uncover its hidden connections.
And to our listeners, thank you for joining us on this journey into the world of quantum harmonic analysis and the Berger-Coburn theorem. We hope you found it as insightful and thought-provoking as we did. Until next time, keep exploring the fascinating world of mathematics. Welcome back to the deep dive. You ready to dive into some math today?
Always.
Cool, cool. Let's talk quantum harmonic analysis.
And the Berger Coburn theorem. Should be fun.
Sounds a bit intimidating, though, to be honest.
Well, we're going to break it down, of course. Start with the basics and build from there.
Okay, that makes me feel better. So, where do we even begin with something like this?
Well, I think the Bargmann-Fock space is a good starting point, denoted as $2 Mathematicians. It's kind of like our foundation for this whole discussion.
Right, the Bargmann-Fock space. Now, that's a space of entire functions, right?
Exactly. And they're square integrable with respect to a Gaussian measure. That measure is super important here.
Okay, I'm vaguely remembering this from my math classes. But remind me again, what makes the Bargmann-Fock space so crucial for understanding the Berger-Coburn theorem?
It's got this really nice structure. It makes it perfect for studying Toeplitz operators.
Ah, Toeplitz operators.
Yeah.
Those are key players in the Berger-Coburn theorem, aren't they?
You bet. So a Toeplitz operator, we denote it as Tapler-X on the Bargmann-Fock space.
Okay.
And it's defined using what we call a symbol. Just another function, we denote it as a
All right, tape the symbol. Got it.
formally, you'd write it as TAFE PAF Z for all $60 in Math BBC.
Okay, so that's how it's defined. But in plain English, what does it actually do? What's the intuition behind a Toeplitz operator?
It's essentially a way to combine multiplication by the symbol with this projection operator. That dollars, by the way, it projects from Toeplitz dollars onto our Bargmann-Fock space.
So we're projecting onto our playground, the Bargmann-Fock space.
Exactly. Now, the interesting thing about Toeplitz operators is that even if the symbol is unbounded, the operator itself to Tep can still be bounded.
Bounded even if its symbol is unbounded. That's strange. How's that possible?
That's precisely what the Berger-Coburn theorem helps us understand. It tells us when this seemingly counterintuitive phenomenon occurs.
Okay, starting to get a sense of the puzzle here. But how does quantum harmonic analysis fit into all of this?
Well, QHA, as we call it for short, gives us a whole new way to look at these concepts. Like, imagine you have a pair of glasses that let you see things from a totally different angle.
Okay, I like that analogy.
Yeah.
So QHA is like a new lens for viewing these mathematical objects.
Exactly. It takes ideas from classical harmonic analysis, things like translations and convolutions of functions.
Right, right.
And it adapts them to the world of operators. So instead of shifting and blending functions, we're shifting and blending operators, specifically on the Bargmann-Fock space.
Operators instead of functions. Got it. Can you give me a concrete example of how that works? How do you, say, translate an operator?
Sure. In classical harmonic analysis, if you want to translate a function, like phi value, by a value of y, you just shift the input.
Check.
5x, y. Simple.
Right. Pretty straightforward.
Now, in QHA, we translate an operator, let's call it a complex number, say $7. The formula is ACH, where UA is a special kind of unitary operator.
Okay, so we're still shifting, but now we're using these unitary operators to do it in the world of operators. What about convolution? How do you convolve two operators?
Good question. So convolution in QHA, well, it also involves an integral, but instead of integrating over numbers, we integrate over these translated operators.
Oh, that's getting a bit abstract.
It is a bit. For instance, imagine convolving an operator, let's stick with ZMSD, with a function LZS. It looks like this, where that DMZ is the Lebesgue measure on Math BBC.
All right, I'm trying to keep up. So QHA is giving us this whole new toolbox for manipulating operators, right?
Yeah.
Shifting them, blending them. But how does it connect back to our Toeplitz operators? That's what we're trying to understand, right?
Absolutely. And here's where things get really cool. QHA shows us that a Toeplitz operator can actually be thought of as a convolution. Specifically, it's the convolution of its symbol with a very special operator.
Okay, that's got to blow my mind. So this seemingly complicated Toeplitz operator can be viewed as a simple convolution.
In a way, yes. We represent it as $2 equals a phi, where equals is the symbol, and phi is this special operator constructed using the reproducing kernel of the Bargmann-Fock space.
So the reproducing kernel's involved too. This is getting pretty deep.
It is, but it's this connection that allows us to leverage the power of QHA to analyze Toeplitz operators. It's like we found a secret passageway into their inner workings.
I love that analogy. So we've got the Bargmann-Fock space as our playground, Toeplitz operators as our main characters, and now QHA as our secret weapon for understanding them. Where do we go from here?
Well, there's another key player we need to introduce, the operator heat semigroup. This is where things get even more interesting.
The operator heat semigroup. I'm intrigued. Tell me more.
It all starts with the heat kernel, that classic idea from analysis.
Oh, yeah, I remember the heat kernel. It's like it describes how heat spreads out over time, right?
Exactly. But here's the twist. We're going to create an operator version of it. It's like taking that heat diffusion concept and lifting it to the world of operators.
An operator heat kernel. Okay, I'm curious. How does that work?
Well, we end up with something called the operator heat semigroup. It's a family of operators denoted as 2 figure 12, where each village all is, get this, a Toeplitz operator.
Wait, so each element of this operator heat semigroup is a Toeplitz operator?
Yep. And the symbol for each philatause is just the standard heat kernel function, collect tool. It's like we're connecting the world of heat diffusion to the world of Toeplitz operators.
Okay, my mind is officially blown. So we've got this operator heat semigroup. Each element is a Toeplitz operator with the heat kernel as its symbol. How does this help us understand the Berger-Coburn theorem?
Ah, the million-dollar question. Remember, the Berger-Coburn theorem links the boundedness of a Toeplitz operator to the behavior of its symbol under heat flow. And that heat flow is captured by the Toeplitz transform.
Right, the t-Berezin transform. It tells us how the symbol changes as we apply this heat flow, right?
Precisely. And here's the crucial part. The t-Berezin transform can actually be expressed using this operator heat semigroup. For t-frac1, it turns out that the t-Berezin transform is just the convolution of the Toeplitz operator with a specific operator from the semigroup.
A convolution with the operator heat semigroup? Wow, it all seems to be coming together. Can you write down that relationship for me?
Sure thing. It looks like this. BTA, 51. So we convolved the Toeplitz operator, t pro bear, with the operator 51 from the semigroup.
Okay, I'm seeing how the operator heat semigroup is becoming a central tool for analyzing these concepts.
It is. Now let's finally talk about what the Berger-Coburn theorem actually states. It has two parts. The first part says that if a Toeplitz operator, a t-ber, is bounded, then its t-Berezin transform, Berger oper, is also bounded for all frac 21.
Okay, so if the Toeplitz operator is well-behaved, its t-Berezin transform can't go crazy. That makes sense. But how do we actually prove that using QHA?
Well, we just saw that DTA is a convolution, right?
Right.
That means we can use what's called QHA Young's inequality. It basically says the norm of a convolution of operators is bounded by the product of the trace norm of one operator and the operator norm of the other.
So we can bound the t-Berezin transform by bounding something else.
Yep. We can write it like this. TA51, TT1, that double bar with the T subscript, that's the trace norm.
Right, the trace norm. Okay, so now we just need to figure out the trace norm of PT1.
And luckily for us, we have a formula for that. From our source material, we know that for frac 51, TT1.
So we plug that in, and boom, we've got our bound for the t-Berezin transform. That's pretty neat. Now, what about the second part of the Berger-Coburn theorem? What does that tell us?
The second part goes the other way. It says if the t-Berezin transform, BTAA, is bounded for some $0 SME frac 1, then the Toeplitz operator is bounded as well.
So this time, the boundedness of the t-Berezin transform implies the boundedness of the Toeplitz operator. How do we prove that one?
It's a similar idea, but with a little twist. This time, we represent the Toeplitz operator, to, as a convolution of the t-Berezin transform with a different operator from the heat semigroup.
Trick 2. We're using a negative parameter now. Is that allowed?
It is, but we need to be careful. Remember, these operators in the heat semigroup are only trace class for frac 2. If 2 hits frac 2, things get a bit messy.
So we're playing with fire here, dancing right on the edge of where the operator heat semigroup behaves nicely.
Exactly. But as long as we stick to $0 CM we're good. Phi t is still trace class, and its convolution with a bounded function like BAT gives us a bounded operator.
And that bounded operator is our Toeplitz operator, 2, 3. I'm starting to see the pattern here.
It's all about cleverly using convolutions and QHA Young's inequality. And just like before, we can get a specific bound on the norm of Tito using the trace norm of phi e.
Which is frac 1. I remember correctly.
You got it. So there you have it, both parts of the Berger-Coburn theorem elegantly proven using the power of quantum harmonic analysis.
I have to admit, I'm really impressed by how concise and elegant these proofs are. QHA really is a powerful tool.
It is. And it goes way beyond the Berger-Coburn theorem. It can be used to understand other aspects of Toeplitz operators, like their Schatten class membership and their compactness. But that's a story for another time.
So you mentioned Schatten class operators and compactness. What are those all about?
Schatten class operators, well, they're like a way to measure how nice a compact operator is.
Nice. Okay, I'm intrigued. Tell me more.
Well, in simple terms, a compact operator kind of squishes things in a certain way. A bounded set gets mapped to a set whose closure is compact.
So it makes things more compact in a sense.
Exactly. Now, Schatten classes take that idea further. They classify compact operators based on how quickly their singular values shrink. The faster those values decrease, the nicer the operator is considered to be.
Okay, so it's all about how quickly things shrink. The faster, the nicer. Got it. How does this relate to Toeplitz operators, though?
Well, there is a fascinating connection. It turns out that the compactness of a Toeplitz operator is closely tied to the behavior of its symbol at infinity.
The symbol at infinity. So we're looking at what happens to the symbol as we move far, far away from the origin.
You got it. And there's a theorem that states this connection quite elegantly. It says that a densely defined Toeplitz operator is compact if and only if its Toeplitzian transform vanishes at infinity.
So if the Toeplitzian transform goes to 0 at infinity, the Toeplitz operator is compact. That's a pretty strong link.
It is. And you know what's really cool? QHA can be used to prove this theorem quite elegantly. It also helps us understand the Schatten class membership of Toeplitz operators.
So QHA is back in action, shedding light on these depot properties. Can you give me an example of how QHA helps with Schatten classes?
Sure. It lets us relate the Schatten norm of a Toeplitz operator to the L dollar norm of its t-Berezin transform. For instance, if you have $1 labor and LP, you get this neat inequality. Tatlek CT LP.
Okay, break that down for me. What does that inequality actually mean?
Well, Tesseras represents the Schatten norm of the Toeplitz operator. The Playt-AL is the L-Baller norm of its t-Berezin transform. That tau is just a constant that depends on tau.
Right. So what's the takeaway here?
It basically tells us that if the t-Berezin transform belongs to the L-tau space, then the Toeplitz operator belongs to the Schatten Plaque class. And we even get a bound on its Schatten norm.
So the behavior of the t-Berezin transform directly influences the Schatten class membership of the Toeplitz operator.
Exactly. And there are similar results for other ranges of 2. QHA provides this amazing framework for quantifying the size of a Toeplitz operator and understanding its finer properties.
I'm seeing that QHA is more than just a clever trick. It's like a powerful lens that reveals the hidden structures and connections within these mathematical concepts.
It really is. And the beauty is we're still just scratching the surface of what QHA can do. There's so much more to explore.
This has been an incredibly enlightening journey into the world of quantum harmonic analysis and the Berger Coburn theorem. I'm truly amazed by how QHA connects these seemingly disparate concepts and simplifies complex proofs.
It's been a pleasure diving deep into these topics with you.
Thank you so much for joining us on the Deep Dive. And to our listeners, thank you for coming along on this mathematical adventure. Be sure to check out the show notes for more resources on QHA, the Berger Coburn theorem, and all the fascinating things we talked about today. Until next time. All right, welcome back, everyone. Ready for another deep dive.
Definitely. Always ready to explore some fascinating math.
And today we're going deep into the world of quantum harmonic analysis, and more specifically, how it's used in operator theory.
Sounds intriguing. What paper are we dissecting today?
This one is titled, A Quantum Harmonic Analysis Approach to the Berger Coburn Theorem.
Ah, the Berger Coburn theorem. Classic. What caught your eye about this paper?
You know, it's the way they use quantum harmonic analysis, or QHA, to kind of simplify the proof of this well-known theorem about Toeplitz operators.
Oh, yeah. It's remarkable how QHA brings this elegant new perspective, and to a problem that's usually been tackled with, well, heavier machinery like pseudo-differential operators.
All right. Totally agree. So we're in the Bargmann-Fock space, right?
Yes, the Bargmann-Fock space.
That's our playground for today. For those who may have forgotten, it's where our functions are entire and square integrable with respect to that Gaussian measure. And then, of course, we have our Toeplitz operators. They're essentially projecting functions onto this space. The paper really digs into some pretty deep questions about those operators. Boundedness, compactness, even their Schatten class membership.
It's like taking this familiar mathematical object and examining it under this powerful new microscope.
Exactly. What's always intrigued me about Toeplitz operators is, well, their boundedness.
Yeah.
It's not just about the boundedness of the function itself.
Right. There are definitely Toeplitz operators out there with unbounded symbols that are, well, still bounded. Characterizing that exactly when that happens, that's been a bit of a puzzle for a while.
A puzzle indeed. Berger and Coburn, they They took a stab at this way back when.
They did, using that heat flow of a function,
Yeah.
also known as the t-Berezin transform.
Ah, the t-Berezin transform.
They made some progress,
Yeah.
definitely.
But a complete picture,
Yeah.
still elusive. That's where this paper comes in, right? It's like, it's wielding the power of QHA, revisiting that Berger Coburn theorem. And it tackles those lingering questions about compactness and Shannon-class membership, all through this new QHA lens. But before we get too lost, maybe a little QHA refresh is in order. For those who haven't had their morning coffee with QHA theorems lately, what are those core concepts at play here? You know, the basics.
Okay, so at its heart, QHA is all about the translation and convolution of operators. Think of it as, well, as manipulating these operators within the Bargmann-Fock space.
So getting hands-on with those operators.
Exactly. QHA translation, that's like shifting the operator around. And convolution, that's like blending it with a function or even another operator.
I like it. Like we're taking these abstract mathematical objects and we're putting them in a blender.
Precisely. And the really fascinating part is how these convolutions tie in with that Berezin transform. You know, the one we mentioned earlier?
Yeah, I remember.
Well, Fulsche's work. It revealed this really profound connection, the set of all Toeplitz operators. With bounded symbols, it's the exact same as the set of bounded uniformly continuous operators.
Oh, hold on. So they're equivalent.
Yes. And that equivalence opens up a whole new way of understanding these operators.
That's amazing. It's like discovering this hidden bridge between two seemingly separate math worlds.
Right.
Okay. So we've got the Bargmann-Fock space, we have these intriguing Toeplitz operators, and we've got the power of QHA. Where does this paper take us from here?
Well, now we delve into something called the operator heat semigroup, denoted by Worist, and it behaves very similarly to the function heat semigroup, you know, the one that applies the heat kernel to a function.
Ah, yes. The heat kernel. So the operator heat semigroup is like applying the heat kernel, but to an operator instead of a function.
Exactly. And just like with its function counterpart, solves the operator heat equation, which describes how an operator evolves over time under the influence of a heat flow.
Okay, got it. Heat flow. What else?
Well, the authors, they extend the definition of vet to negative values of t. They use this formula, a tet et2, 10 art 0, where S is that Laplacian operator on the Bargmann-Fock space, and that extension unlocks some really interesting properties.
Okay, so it's like we're extending the definition. We're going beyond the usual limits. What kind of properties are we talking about here?
Well, that's where proposition 3.2 comes in. This proposition highlights some crucial properties of it, particularly the fact that for T12, it's a trace class operator.
Trace class, okay. Remind me, what makes those operators so special again?
Of course. A trace class operator is a compact operator where the sum of its eigenvalues converges absolutely.
Right, okay, I remember those.
They're remarkably well behaved. Several properties that are well exploited throughout this paper. And proposition 3.2 tells us that for T12, this is always trace class. It also gives us a formula for its trace norm, a measure of its size in a specific sense. Set 1R, 1 plus Tn for T12. This bound. It's crucial for some later results.
Got it. So we have our operator heat semigroup. We know it's trace class for certain values of T. And we have a way to measure its size. What's next?
Now, the paper really dives into densely defined operators within that framework of QHA. It gets pretty intricate here.
Okay.
They define this linear subspace D, which is essentially the domain of those densely defined operators.
Okay. So, like, D is a special club for those operators.
Exactly. That's where they live and operate. Remember how we talked about convolving operators with functions in QHA?
Yeah, I remember. The blender.
Right. Well, the authors, they extend that idea to densely defined operators, giving clear conditions for when such a convolution is even possible, making sure everything is well defined.
Okay, I'm following so far. And this connects back to our Toeplitz operators, right?
You bet. Proposition 4.2 is where the magic happens. It states that Toeplitz operators with symbols from a particular class of functions denoted A2, they're densely defined on D. And what's more, it connects them. These Toeplitz operators can be expressed as convolutions within the QHA framework.
So we're seeing Toeplitz operators through this QHA lens. This is getting good. Tell me more about those functions in A2. What makes them special?
Okay, so these are functions that, when you shift them around the Bargmann-Fock space, they remain square integrable with respect to, you guessed it, the Gaussian measure.
Gaussian measure, always popping up.
Formally, a function A belongs to A2 if ACA, EC2 for all S2. Essentially, they're well behaved enough to ensure that the associated Toeplitz operators are densely defined on D.
All right, makes sense. Any specific examples of these densely defined Toeplitz operators in the paper?
Yes. There's a particularly intriguing one. It involves a natural extension of the heat kernel, denoted Rick, where is a complex number. This, much like the heat kernel itself, it has this Gaussian form, but it's generalized. It's wax2 plus 1, xp ace2 plus 1.
Interesting. What's so special about this example? Why is it included?
The paper shows that torf, that's the Toeplitz operator, associated with this extended heat kernel, it's densely defined on D or its boundedness, it depends on the specific condition, 1 plus 1 hour 1. Meaning, for certain values of walks, the output of this Toeplitz operator can just, well, grow without bound.
Ah, so even with this seemingly simple example, we're running into those subtleties of boundedness.
Exactly. It really highlights how important it is to understand the exact conditions for when these densely defined Toeplitz operators behave, well, nicely.
Nicely. I like it. Anything else about this example?
Yes. The example also shows that tet, which is a Toeplitz operator associated with a particular real value, is bounded if and only if 2 min x 12. Interestingly, within this range, tet is identical to et-het. Our operator heat semigroup.
Whoa, hold on. Our operator heat semigroup is showing up here.
It is.
It's like all these concepts are starting to weave together.
And the connections, they continue. The paper revisits the Berezin transform. And they show it can be defined for these densely defined operators.
Wow.
And crucially, it keeps its injectivity, meaning if two densely defined operators have the same Berezin transform, they got to be the same operator.
That's incredibly useful. Like it's a fingerprint. We can identify those operators.
It is.
We've covered a lot here. QHA, operator heat semigroup, densely defined operators, and the Berezin transform. I'm ready to see how it all comes together to tackle that Berger Coburn theorem.
Yeah.
And those related questions.
Are you?
Absolutely. That's where we'll pick up next time. Welcome back to our deep dive. Last time we laid the groundwork with QHA, the operator heat semigroup, and those densely defined operators. And now we're ready to tackle the Berger Coburn theorem.
Alrighty, I'm looking forward to this. This theorem, it attempted to characterize bounded Toeplitz operators using the heat flow of their symbols.
Exactly. But before we dive into the theorem itself, the paper establishes this crucial link between the heat flow of a Toeplitz operator and our trusty operator heat semigroup.
I knew it. The operator heat semigroup takes center stage.
It does. Proposition 5.1 states that for T12 and for a symbol A that belongs to our special function class A2. If the Toeplitz operator toe is bounded, then the t-Berezin transform of A, which represents that heat flow, it can be expressed as a convolution.
A convolution involving Ta and our operator heat semigroup, I'm guessing.
Exactly. It's Ta convolved with A2, where, as you might recall, represents our operator heat semigroup.
Convolutions everywhere. It's like the glue holding QHA together.
It's fundamental. Okay, so now with this connection, we're ready to tackle the Berger-Coburn theorem itself. It's stated as theorem 5.2 in the paper.
All right. Hit me with it. What does this theorem tell us? I'm ready.
It has two parts. The first part states that if a Toeplitz operator, Ta, is bounded, then the t-Berezin transform of its symbol A is also bounded for all T12. Furthermore, it gives us this upper bound for the norm of that t-Berezin transform.
Okay, so give me the inequality.
It's AT-T, where CT is a constant depending on pot and T.
Okay, I see. So the boundedness of the Toeplitz operator, it influences the boundedness of its heat flow.
Indeed. But the second part of the theorem, even more interesting. It states that if the t-Berezin transform of A is bounded for some to between 0 and 12, then, well, surprisingly, the Toeplitz operator Te is bounded.
It goes both ways. Bounded heat flow implies a bounded Toeplitz operator. Now, that is elegant.
It is. And it gets better. The theorem actually provides an explicit formula for the bounded extension of Te in this case.
An explicit formula. All right, tell me more. What does it look like?
Another convolution. The bounded extension of Te is given by Te equals A. Remember, a PAVE is our operator heat semigroup evaluated at odd T, which we know is well defined, and trace class for T between 0 and 12.
Wow, so the operator heat semigroup, it's not just theoretical. It's actively involved in constructing these bounded extensions. I'm guessing there's an inequality relating the norms here, too.
You know it. The theorem states Te AE, TA, TAA.
Wow. This theorem is a powerhouse. It connects boundedness, heat flow, and it even gives us these explicit constructions. It's amazing.
And the proof, using QHA, remarkably concise and elegant.
The right tools for the job.
Okay.
We've revisited the Berger-Coburn theorem. What other mathematical treasures does this paper have in store for us?
Well, the paper then ventures into the realm of Schatten class operators.
Oh, yes. Schatten class operators. What about them?
A special class of compact operators with some nice properties. The paper presents a quantitative version of the theorem that characterizes their Schatten class membership of Toeplitz operators.
Okay, so we're going even deeper into this world of compact operators.
We are. Theorem 5.3 is a gem. It kind of mirrors the structure of the Berger-Coburn theorem, but it focuses on Schatten class membership instead of just boundedness.
So instead of asking, is it bounded, we're asking, what kind of compact operator is it?
Precisely. And just like before, the theorem has two parts. The first part states that if a Toeplitz operator, tau, belongs to the Schatten P-class, then the t-Berezin transform of its symbol A belongs to the LP space. For all T12, it also provides an inequality, ATPE T-top.
So membership in the Schatten P-class for tau, it translates to membership in the LP space for the heat flow.
Yes. And the second part, as you might expect, goes in the reverse direction. It states that if the t-Berezin transform of A belongs to the LP space for some top between 0 and 12, then the Toeplitz operator ta belongs to the Schatten P-class.
I'm sensing a pattern here. It's very elegant.
Patterns in math are beautiful. And just like in the Berger-Coburn theorem, we get that explicit formula for Te in terms of, you guessed it, a convolution, Te AT.
That operator heat semigroup. It's the gift that keeps on giving.
Yeah.
I bet there's an inequality relating the norms in this case as well.
You bet. The theorem states, tap, C, ATT.
This theorem feels like a powerful extension of that Berger-Coburn result.
It is.
It gives us such fine-grained control over those Toeplitz operators.
And to top it off, the paper answers a question raised in previous work by providing those quantitative estimates.
I love how this paper not only revisits these classic results, but it pushes the boundaries of our understanding.
It really does. It's a testament to the power of QHA.
QHA.
Now, with all this talk about Schatten class operators, we can't forget about another important type of compact operator. Compact operators in general.
Right. Those are the operators that, roughly speaking, they squeeze the space they act on.
Good way to visualize it. Theorem 5.4 in the paper, it characterizes the compactness of those densely defined Toeplitz operators. Okay.
So we're moving from specific types of compact operators to compactness in general.
Exactly. And guess what plays a key role in this characterization?
I'm going to go with the t-Berezin transform. It's the star of the show.
You got it. The theorem states that if Ti is compact, then the t-Berezin transform of A belongs to the space of continuous functions that vanish at infinity, denoted by C0 for all T12.
Vanishing at infinity, meaning as you move farther and farther out in the complex plane, these functions kind of fade away.
Precisely. And the converse also holds. If the t-Berezin transform of A belongs to C0 for some tart between 0 and 12, then the Toeplitz operator Ti is compact.
Okay. This feels like a nice counterpart to the previous theorems.
Yeah.
Connecting compactness to the behavior of that heat flow.
It is. And the proof. Once again, it showcases the elegance of QHA. It completely bypasses the use of pseudo-differential operators, which were, well, traditionally used in proofs of similar results.
It's like QHA provides this clean, almost intuitive way of looking at these problems.
It does, doesn't it?
I'm really starting to appreciate its power. Okay. Where do we go from here?
Well, we've explored the Berger-Coburn theorem, delved into that Schatten class, and characterized compactness. The paper concludes by revisiting some specific examples, providing a deeper look at these concepts in action.
All right. I'm eager to see how these examples bring everything together. This deep dive has been pretty mind-extending so far.
It has been, hasn't it? We'll continue our exploration of those fascinating examples in the next part of our deep dive.
Welcome back, everyone. We're on the final leg of our deep dive today. And, we've covered so much already. Berger-Coburn theorem, Schatten classes, the characterization of those compact Toeplitz operators. Now, I'm really curious to see those concepts in action with some specific examples.
Me too. The paper gives a few illuminating ones, and one that ties back to our earlier discussion. It involves that natural extension of the heap kernel.
Ah, right. The one with that the interesting boundedness condition on actor.
Right. Exactly. The paper revisits that example, and it shows that if X satisfies that condition, 1 plus 1 after all, then the Toeplitz operator, it's not only bounded, but it also belongs to every Schatten P-class for P0.
Wow, that's pretty remarkable. This seemingly, well, simple extension of the heat kernel.
Hmm.
It leads to this Toeplitz operator with such well-behaved properties.
It does, and the proof, it leverages a lot of the tools we've been talking about, QHA convolutions, the operator heat semigroup, properties of those trace class operators. It really illustrates how those concepts, they harmonize to reveal these deeper insights.
It's like we started with this intriguing object, and we built this whole mathematical framework around it, and now we're back to pick with this much richer understanding.
Right. It really speaks to how interconnected mathematical ideas are. Exploring these seemingly disparate concepts often leads to, well, unexpected connections, profound connections, really.
This whole deep dive has been a perfect example of that. We started with this paper, right, about QHA and Toeplitz operators, and we've journeyed through this universe of mathematical concepts, Bargmann-Fock spaces, the heat kernel, operator semigroups, Schatten classes, and so much more.
It's been a real pleasure navigating this landscape with you.
Likewise. And to our listeners, I encourage you to keep exploring. QHA is powerful. It has applications beyond, beyond anything we've even touched on today. Who knows what you might uncover.
Remember the world of math. Vast and interconnected. Each discovery, it unlocks new avenues for exploration.
Well said. And with that, we conclude our deep dive into the world of QHA and Toeplitz operators. Until next time, keep those mathematical minds curious. Welcome back to the show. Today we'll be taking a deep dive into the world of Toeplitz operators on the Bargmann-Fock space.
Yeah, it's a really fascinating area, where complex analysis, operator theory, and even quantum mechanics kind of all come together.
Absolutely. There are even some surprising connections to signal processing in there, too.
Right. And what's particularly interesting is how this recent paper by DeWage and Mitkovsky uses this really powerful tool called quantum harmonic analysis, or QHA for short.
Yeah, QHA.
Yeah, to kind of simplify and clarify some of the, the classic results in this area, especially the Berger Coburn theorem.
I was really impressed by how their approach not only, streamlines existing proofs, but also gives us this, whole new perspective on the relationship between Toeplitz operators and their symbols.
Definitely. To really appreciate what they've done, maybe we should start with a quick overview of the kind of key players involved here.
Yeah, let's do that.
So the Bargmann-Fock space, which is denoted by two thoglars, the CSEC DIL, that's the space of entire functions on CNO that are square integrable, with respect to this Gaussian measure, pi dvz. And just to clarify, dvz is the Lebesgue measure on CNEA.
Right. So we're dealing with these, well-behaved entire functions, the ones without any singularities, right?
Exactly.
Living in this kind of special space that's equipped with this Gaussian weight.
Precisely.
It's almost like you're giving preference to functions that are more concentrated around the origin.
Yeah, you can think of it that way. Now, a Toeplitz operator on this space, we denote it by Teuler, is defined as TAF, P until dollar. So here is a bounded measurable function, and we call that the symbol of the operator.
Okay.
$5 is a function in $3, and $2 is the orthogonal projection from L2CN onto TCN. So it's kind of projecting from this larger $2 space down to our Bargmann-Fock space.
So the symbol function, it's like, in a way, it's modulating the function it acts on, right?
Yeah, that's a good way to think about it. It's like it's, shaping the function in a particular way.
Now, I remember that the boundedness of the symbol, whether it's a bounded function or not, it doesn't necessarily mean that the Toeplitz operator itself is bounded, right?
That's exactly right. That's one of the kind of tricky things about Toeplitz operators, the Berger Coburn theorem. That's kind of the, the star of the show here.
Yeah.
That gives us a really nice connection between the boundedness of Toeplitz and the behavior of this thing called the t-Berezin transform of the symbol.
Ah, yes, the Berezin transform. I haven't really worked with that in a while. Could you, maybe remind us how that's defined?
Sure, yeah. So for a function, a Lar line, it's a t-Berezin transform, which we denote by wide tilde, is defined as wide 2 LAA T Kobe 2, where 2 LAA is the reproducing kernel of 2 Perez 2 pillibers dollar, where Toeplitz is the reproducing kernel of t-Berezin in dollars. It's normalized so that the norm of 2 Dieller and 2 Tobers is 1,
Okay, so it's basically like a weighted average of the symbol function, right?
Or
Where the weights are given by, like, the modulus squared of this reproducing kernel.
exactly. It's kind of like, smearing out the symbol in a particular way.
So how does this Berger transform tie into the boundedness of the Toeplitz operator?
Okay, so the Berger Coburn theorem, it basically tells us that for 12 $2, if Flaws is bounded on 2 through bill, then y tilde is bounded on $7, and we have this inequality. The supremum norm of y tilde is less than or equal to times the operator norm of 2 pound. So that's kind of one direction.
Okay, yeah.
And conversely, for $0, 12 2, if y tilde is bounded, then 2 is bounded, and we have this other inequality. The operator norm of tildes is less than or equal to the supremum norm of y tilde dollar.
So is it like a two-way street?
Right.
The boundedness of the Toeplitz operator is tied to the boundedness of its transform symbol, the Berger transform. But what about when Tiller's is exactly 1/2? Is there anything special about that case?
Yes, that's the mysterious case, the one that still keeps mathematicians up at night. The case when T equal 12 2, that's still an open problem.
Wow, that's pretty interesting.
And it's one of the reasons why this whole area is so fascinating. There's still so much we don't know.
Yeah, I'm really curious to hear how Dweji and Minkowski use this quantum harmonic analysis approach. I have to admit, I'm not like super familiar with QHA.
Well, in a nutshell, it's a set of techniques that let us, kind of analyze operators by like translating them and convolving them, kind of like how we do with functions.
Oh,
It's a way of like, looking at operators from a different angle.
okay.
One of the main tools they use is this thing called the operator heat semigroup. We denote it by TUS, and it acts on operators on this 22 space, 2,CN. What's cool is this semigroup can be expressed as a linear combination of projection operators, dtk 2k plus ntpk day, where tp is the projection onto the tand eigenspace, the harmonic oscillator.
So it's sort of like a way to smooth out operators, right? It's kind of analogous to how like the classical heat kernel smooths out functions.
Exactly. And the really neat thing is that this operator heat semigroup, we can actually extend it to negative values of $2.
Oh, really?
Yeah, which gives us this really rich interplay with the Berezin transform.
Okay, this is all starting to come together now. I think I'm ready to like dive into the details of how they actually use QHA to prove the Berger-Coburn theorem. It sounds like there are going to be some like clever manipulations of convolutions and inequalities involved.
You got it. The way they express the Berezin transform as a convolution, which lets them use the QHA-Young's inequality, it's really elegant. Shall we get into the specifics of the proof now?
Yeah, let's do it. I'm really excited to see how this QHA approach unlocks the secrets of the Berger-Coburn theorem.
Okay, so the real beauty of Dweji and Minkowski's approach is like how they connect the Berezin transform to convolution. They show that for a Toeplitz operator, $2, its Tudor-Berezin transform can be expressed as this. Toeplitz te away t klein, and that's for 10, 10, 12, $2.
So they're basically like translating this heat flow of the symbol, which is captured by the Berezin transform, into a convolution in the operator world.
Exactly. And this is where, the power of QHA-Young's inequality really comes into play. This inequality gives us a way to, like, control the norm of a convolution using the norms of the individual components.
Oh, okay.
In this case, it lets them bound the supremum norm of y tilde, which is, our Berezin transform, by the product of the operator norm of Teller and the trace norm of Telta.
Right, so they're cleverly using this inequality to connect the boundedness of the Toeplitz operator to the behavior of this convolution. I like it.
Exactly. And since we know how to compute the trace norm of the operator heat semigroup, they end up with this inequality, y tilde $20 which equals 2t1 tilde.
Wow, that's really elegant. So the first part of the Berger-Coburn theorem for 212 tilde, it just kind of falls out naturally from this convolution representation and the QHA-Young's inequality?
It does. It's pretty neat. Now, the other direction, where $0 to 12 2, it involves a slightly different strategy, but it's like equally insightful. They start by assuming that y tilde is bounded for some dollars in that range. And the goal is to show that this implies that the Toeplitz operator, the Berger, is also bounded.
Okay, so now we're kind of working backwards, right? We're going from a bounded Berezin transform to a bounded Toeplitz operator.
Right, and the key here is that they construct this this new operator, which they define as bital, y tilde. Notice that we're using the operator heat semigroup at a negative value of $2 here.
Oh, right. That's possible because of that that extension we talked about earlier.
Exactly. That extension really comes in handy here.
But I'm a little confused. what is this new operator dollar actually doing? What's its purpose?
So this new operator dollar, it turns out to be a bounded extension of our original Toeplitz operator, $2.
Oh.
And they show this by proving that both bad dollar and dollar have the same Berezin transform, which basically means they must be the same operator.
Ah, I see. So they've sort of like smoothed out the Toeplitz operator using this convolution with the operator heat semigroup.
Precisely. And since we assumed that y tilde is bounded, and we know that it's trace class even for these negative values of dollars, they can use the QHA Young's inequality again.
Right.
And this gives them an upper bound on the operator norm of 2p, which is y tilde at p, and that's equal to 122 tall, where 1 dollar plus 1p evans are on.
Amazing. So both directions of the Berger Coburn theorem are beautifully proven using this convolution representation and the QHA Young's inequality. It's incredible how QHA provides such a streamlined approach.
It really is, and this is like just the beginning. Dewage and Minkowski go on to use QHA to, delve deeper into the properties of these Toeplitz operators. They explore things like their Schatten class membership and their compactness.
Those are definitely topics I'm interested in. Can you tell us a little bit about what Schatten classes are and why they matter in this context?
Sure. So Schatten classes are a way to classify how compact an operator is. An operator $t on a Hilbert space is in the Schatten class, which we denote by safe Peeler if the sequence of its singular values, we usually denote them by lambdage, belongs to the sequence space.
So it's a way to measure how quickly the singular values of an operator decay.
Mm-hmm.
The smaller the Peeler, the more compact the operator is. And compact operators are the well-behaved operators that, in a sense, squeeze infinite dimensional spaces into finite dimensional ones. They're really important in, functional analysis and approximation theory.
Precisely. And when we're talking about Toeplitz operators, their Schatten class membership gives us valuable information about the spectral properties and behavior. Dewage and Minkowski, they actually establish a quantitative link between the Schatten norm of a Toeplitz operator and the all-dollar norm of its t-Berezin transform.
Wow, that's a pretty powerful connection. So they're taking the Berger-Coburn theorem to an even finer level of detail, right? They're looking at how compact the Toeplitz operator is based on its transform symbol.
Exactly. They also revisit a classic result about the compactness of Toeplitz operators, and they offer a much more streamlined proof using, you guessed it, QHA.
No surprise there. It seems like QHA is the key to unlocking a deeper understanding of these operators. Could you give us a little peek into this new proof of the compactness result?
Yeah, so this classic result, it basically says that if the symbol of a Toeplitz operator vanishes at infinity, then the operator itself has to be compact.
Right, right.
And what Dewage and Minkowski do is they offer this really clean and concise proof using, our friend QHA.
I'm not surprised. At this point, QHA seems to be the ultimate tool in this area.
It really is. So for the proof, they kind of break it down into two parts.
Okay.
First, they show that if you have a compact Toeplitz operator, $, then its t-Berezin transform, which is y tilde dial, that's got to vanish at infinity for $2.
Gotcha. So that takes care of one direction. Compact operator implies a vanishing Berezin transform.
Right.
But what about the other way around? How do they show that a vanishing Berezin transform means you've got a compact operator?
Okay, so for that part, they start by assuming that y tilde Broly vanishes at infinity for some $0, $12, $2.
Okay.
And then what they do is they approximate y tilde bile with a function, let's call it baller, that belongs to $C.
You see it, so that's the space of continuous functions that vanish at infinity, right?
Exactly.
So they're finding a nice, well-behaved function that's really close to the Berezin transform.
Right. And the neat thing about this is that the Toeplitz operator that goes with this function, $, so $2, that has to be compact because baller is in C's.
Ah, I see. So if they can show that t-Dals is, kind of close to t-Dollars, then t-Dals itself would have to be compact too.
Exactly. They use some, clever tricks with the heat semigroup and the QHA Young's inequality to show that the difference between t-Dollars and t-Dollars can be made super small.
So that means t-Dollars got to be compact.
Precisely.
Wow, that's another really elegant and intuitive argument.
It is.
It's amazing how QHA can simplify these classic results and, really make them much clearer.
I agree. It's really a game changer for this field.
This whole deep dive has been incredibly fascinating. It's amazing to see how QHA gives us this unified framework for understanding the boundedness, the Schatten class membership, and even the compactness of these Toeplitz operators.
I know. It's it ties all these different concepts together so beautifully.
It really does. So to wrap things up, What would you say is the most important takeaway for our listeners today?
I think the biggest takeaway is that QHA is this super powerful and versatile tool for analyzing Toeplitz operators on the Bargmann-Fock space. It helps us connect these seemingly unrelated ideas: convolution, heat semigroups, Schatten classes, and it leads to these really elegant proofs and, much deeper insight.
Absolutely. It's been a real eye-opener for me. Now, before we go, I want to leave our listeners with a thought-provoking question. Do you think this QHA approach could be used to study other types of operators, beyond just Toeplitz operators?
That's a great question. And to be honest, it's something mathematicians are actively working on right now.
Wow.
The potential applications of QHA are huge.
Definitely.
It's a really exciting area of research, and I think we're going to see a lot of breakthroughs in the near future.
Well, on that note, we'll wrap up this deep dive. Thanks for joining us on this journey into the world of Toeplitz operators and quantum harmonic analysis. Until next time, keep exploring the beauty and the power of mathematics. Welcome back, everybody. Today, we're going to be taking a deep dive into a paper that tackles a pretty classic theorem in operator theory.
Okay.
It's the Berger-Coburn theorem. But what's really cool about this paper is the approach it uses: quantum harmonic analysis.
Yeah, it's definitely a different way of looking at it, a fresh perspective.
The paper's called A Quantum Harmonic Analysis Approach to the Berger-Coburn Theorem.
All right.
And just from that title, it promises a simplified proof using QHA, specifically for densely defined operators.
Right.
So let's jump right in. I think we should start with the abstract on page 1.
Sounds good.
Okay, so the abstract states that basically what they're trying to do is present this simplified proof of the Berger-Coburn theorem,
Okay.
but using QHA specifically for these densely defined operators. Now, I think before we get too far into the weeds here, it would be helpful to take a step back and kind of consider why this QHA approach is so significant.
Absolutely. I think, we're all pretty familiar with the Berger-Coburn theorem and what it means for Toeplitz operators. But the traditional proofs can get really complex. They often use pseudo-differential operators, which can be...
Yeah, a bit of a headache sometimes.
Exactly. So what's really cool about this paper is that it uses this framework of quantum harmonic analysis to give us a more elegant, and I even say more intuitive way to prove this theorem.
I like the sound of that.
Yeah.
So how does QHA simplify things, especially when you're dealing with these densely defined operators?
So QHA basically lets us take advantage of the inherent structure of the Bargmann-Fock space, which, as you know, has these deep connections to quantum mechanics. And remember, the Bargmann-Fock space is like the natural setting for these Toeplitz operators.
Okay.
By looking at these operators through the lens of QHA, we can use these really powerful tools like convolution and translation,
Interesting.
which are kind of inspired by concepts from quantum mechanics.
So it's like we're using the language of quantum mechanics to understand operator theory.
Exactly. And when we're dealing with densely defined operators, which we know aren't defined on the entire Bargmann-Fock space, QHA provides a framework to extend those operations and analyze their behavior in a much more controlled way.
Okay, so QHA isn't just about simplifying the proof. It's also about giving us better tools to work with these more general operators.
Exactly. It opens up all these new ways of understanding how these Toeplitz operators behave, especially the ones with unbounded symbols.
Now, the paper also mentions that it looks at some related topics like compactness and Schatten class membership of these operators. It seems like QHA has a pretty wide reach here.
Definitely. It really does. The authors use it to shed new light on these properties, and they offer clearer and more concise proofs for them.
Very cool.
We'll definitely get into more of those topics as we go through the paper.
I'm looking forward to it. Let's move on to page 2, where the introduction continues.
Okay.
And they lay out some of the preliminaries.
So on page 2, they start by formally stating the Berger-Coburn theorem itself.
Okay.
And it basically says that if the heat flow of a Toeplitz operator symbol is bounded for some less than 1/2.
Okay. Then the operator itself has to be bounded. And going the other way, if the operator is bounded, the heat flow is bounded for C greater than 1/2.
So the boundedness of this heat flow, whatever that means, tells us something about the boundedness of the operator itself.
Right, exactly. And keep in mind, the heat flow here refers to the t-Berezin transform of the symbol.
Okay.
It's a key concept that we'll see a lot throughout the paper.
Gotcha. They also bring up this interesting open question.
Yes.
They ask, is the Toeplitz operator bounded if and only if that heat flow at T equals 1/2 is bounded?
Right. It's a question that's been around for a while.
Yeah.
Even with traditional methods, it's been tricky. I'm really curious to see if this QHA approach can give us any new insights into this.
Fingers crossed. Okay, let's get into the preliminaries.
Okay.
They start by defining the Bargmann-Fock space, the $2 for sols.
Right. Just as a reminder, it's that space of entire functions on MathBBCN that are square integrable with respect to that Gaussian measure. Of course, of course. And then they introduce the orthogonal projection, PL2, Math 2, BAF.
Right. That projection is really important for defining the Toeplitz operator itself. It lets us project from that larger $2 space onto the Bargmann-Fock space.
Gotcha. Which, of course, brings us to the star of the show, the Toeplitz operator, denoted as key dollars, with the symbol on. And they define that as TAF-DL.
So basically, for a function $5 in that Bargmann-Fock space, we multiply it by the symbol, and then we project the result back onto the Bargmann-Fock space using DAF.
A nice two-step process that captures the essence of the Toeplitz operator.
Yeah.
Then we have the heat kernel, which we know acts as an approximate identity.
Right, and its role will become a bit clearer as we get into the QHA framework and start looking at convolutions.
Okay, cool. And finally, they define the normalized reproducing kernel, $, which is associated with each point in the Bargmann-Fock space.
Right.
What role does this kernel play in the context of QHA?
That reproducing kernel is crucial for defining QHA convolution, which, as we'll see, gives us a powerful way to represent and analyze these Toeplitz operators.
Now things are getting really interesting. I'm ready to go deeper into this QHA and see how it all connects.
Let's do it.
Let's move on to page 3. See what we find.
Okay, page 3 is where they really unpack this quantum harmonic analysis stuff.
Oh, I'm excited.
On page 3, we dive into the heart of the paper, quantum harmonic analysis, and they start by introducing this concept of QHA translation.
Okay, this sounds interesting. How does this translation work in the context of QHA?
Well, it involves using these special operators called while unitary operators. They're denoted as DL, and they basically act on functions in the Bargmann-Fock space and essentially shift them around.
Gotcha.
So for a function 5 or 70c, the QHA translation of Veli by Zeilers is given by while hell baf fe psi deal. So it's like we're shifting the function's perspective, right? We're viewing it from a different point in that complex space. Yeah, exactly. And the paper emphasizes that these while unitary operators are really important for defining the idea of uniform continuity of operators in the QHA framework.
Okay, interesting. What does uniform continuity mean in this setting?
It's basically a way to quantify how smoothly an operator changes as we shift it around using these QHA translations. So an operator $2 is uniformly continuous in the QHA sense if the norm of that difference, WZAT, WZT, approaches 0 as ZR gets closer to 0.
So it's a measure of how stable the operator is under these QHA translations.
Exactly. Then they move on to QHA convolution, which is like a key operation in this whole framework.
Okay.
And they define this convolution between a function and an operator taller, denoted as AT, as AT, as AC, A, DTW is AT.
So we're kind of like averaging the operator $2 over all possible translations.
Right.
Weighted by the function.
Yeah, that's a good way to think about it. They also define the convolution between two operators, ACD day.
Right.
And it's denoted as ZT day. It's given by SDC, SCT, ZT, SW day, SDTC, SW day.
So it seems like convolution is really fundamental in QHA. Right? It lets us combine and manipulate operators in a way that reflects the geometry of that Bargmann-Fock space.
Exactly. And just like with regular convolution, there are some important inequalities that govern the behavior of this QHA convolution.
Right.
And they point out Young's inequalities, which basically give us bounds on the norms of those convoluted objects.
Those inequalities must be super important for understanding the properties of the convoluted operator.
Oh, absolutely. They relate the size of the convoluted object to the sizes of the original function and operator.
Okay.
And they'll play a key role in the later sections when they prove the Berger Coburn theorem.
Gotcha. Now, they then emphasize a crucial link between this QHA stuff and Toeplitz operators, stating that Toeplitz operators can actually be represented as convolutions.
Right. This is a really key insight.
Okay.
They show that a Toeplitz operator, $2, can be written as $2 with the 8 times Kiedeballer way, where 1 times K Pella 2.
Wow. So the Toeplitz operator, which is defined through multiplication and projection, can also be seen as a convolution, in the QHA setting.
Precisely. And this is a really powerful representation because it lets us apply all these QHA tools, like those Young's inequalities we were talking about, to analyze these Toeplitz operators.
That's amazing.
Yeah.
It's like we're translating the problem into a new language where we have a whole new set of tools.
Exactly. And they also briefly discussed that Berezin transform that you mentioned earlier.
Okay, right.
They define it for functions and operators, and they highlight its relationship to this QHA convolution.
Can you remind us how the Berezin transform is defined?
Sure. So for a function $5, the Berezin transform, denoted as tilde, is defined as tilde's Langle, FKZ Kiel's wrangle. It's essentially averaging the function over a small disk centered at cell O using the reproducing kernel.
Gotcha.
And for an operator, the Berezin transform, denoted as tilde, is defined as tilde Langle-Silde, which basically captures how the operator acts on that reproducing kernel at $0.
So it's a way to look at the function or operator's behavior locally.
Right. And the key point they make is that this Berezin transform can actually be expressed using QHA convolution.
Interesting.
They show that tilde psi IC is another specific operator.
So we have this connection between the Berezin transform, which has its own geometric meaning, and QHA convolution, which is like the heart of our QHA framework.
Exactly. And this connection is crucial for understanding how these operators and their symbols behave, especially when we start looking at that Berger Coburn theorem. It lets us move between these different perspectives and really understand the interplay between the operator, its symbol, and that heat flow.
It's really cool how all these pieces are starting to fit together. We've got the QHA, the convolution, and the Berezin transform. I'm excited to see how they use all this to tackle the Berger Coburn theorem.
Me too. Let's turn to page 4. And that's where they introduce this thing called the operator heat semigroup.
The operator heat semigroup. Okay, that sounds a little familiar.
Yeah.
Isn't there a heat semigroup for functions too?
You're exactly right.
How does this operator version relate to that?
There is that well-known heat semigroup for functions.
Right.
And it describes how a function evolves over time according to that heat equation. This operator heat semigroup is similar.
Okay.
But instead of acting on functions, it acts on operators.
So it's like watching a movie of operators changing over time.
Exactly. And they define this operator heat semigroup denoted as ETL.
Okay.
And they show that it satisfies a particular heat equation.
That's cool. What's the significance of this operator heat semigroup for the Berger Coburn theorem?
Well, remember the Berger Coburn theorem involves the heat flow of the symbol, which is that t-Berezin transform.
Yes.
The key insight here is that this operator heat semigroup gives us a way to express that t-Berezin transform differently. They show that the t-Berezin transform of an operator dollar can actually be written as tilde TTETL.
So the heat flow of the operator is like a convolution of the operator with this evolving heat semigroup.
Precisely. And this is super helpful because it lets us analyze that heat flow using the properties of this operator heat semigroup, which are much easier to work with.
That makes sense. It's like finding a new way to look at the heat flow that reveals its structure.
Exactly. They then go into some key properties of this operator heat semigroup in propositions 3.1 and 3.2.
Oh, okay. What do those propositions tell us?
So proposition 3.1 gives us an actual formula for this operator heat semigroup.
Right.
They show that ETLHT is a specific function that's connected to the heat kernel.
So the operator heat semigroup itself is expressed as a convolution involving that heat kernel.
Exactly. And that formula is really useful because it means we can calculate this operator heat semigroup for different values of Toller's out.
That's handy. Now, what about proposition 3.2?
So, proposition 3.2 highlights a couple of important properties of the operator heat semigroup.
Okay.
First, it shows that this operator heat semigroup kind of acts like a semigroup, even though it's not exactly one.
So there's still some algebraic structure there.
Yeah, exactly. It's enough for our purposes.
Okay.
And second, proposition 3.2 shows that the trace norm of these operators is well behaved for $2 YALs. They prove that the trace norm of ETDLL is bounded by a constant times TD dollar.
This trace norm behavior is interesting. What's the significance of that bound?
That bound is important because it means that the operator heat semigroup doesn't blow up as $T$ gets close to 0.
Okay.
And that's really important for looking at the heat flow near TD dollars,
Gotcha.
which is a bit of a tricky point in the Berger-Coburn theorem.
I see. So this bound makes sure that our analysis stays on track even near that critical point.
Exactly. Now, on page 5, they switch gears a bit and focus on densely defined operators.
Right.
Remember, those are operators that aren't defined on the entire Bargmann-Fock space,
Right.
just on a dense subset. Okay.
And we know that not all Toeplitz operators are bounded. Some have unbounded symbols, which gives us those densely defined operators.
Right. And the goal of this paper is to give that simplified proof of the Berger-Coburn theorem for those more general, densely defined Toeplitz operators.
Exactly. So how do they extend this whole QHA framework to work with these densely defined operators?
It's a good question. How do they do that?
They introduce this special class of symbols denoted as A lambda,
Okay.
and they show that Toeplitz operators with symbols in this class are densely defined on that Bargmann-Fock space.
So these A2 lambda symbols are like our key to making these densely defined Toeplitz operators.
Right. And then they go on to analyze the convolution of these symbols with those heat kernels.
Right.
Which, if you remember, are super important for the QHA approach.
Okay, so what do they find out about these convolutions?
In proposition 4.1, they show that if A belongs to O lambda for some lambda doll, then a fit is well defined. And it also belongs to A to lambda for all TLer. So convolving those special symbols with a heat kernel keeps everything within that same class of symbols.
Exactly.
Which ensures that the resulting operators are still densely defined.
Right. That's a key step in making sure QHA works in this setting.
Gotcha. They then establish this connection between the densely defined Toeplitz operators and convolution in proposition 4.2.
Yeah.
What does that proposition say?
It says that if I belongs to all lambda for some lambda dollars, then that densely defined Toeplitz operator ta can be represented as two dolls, can be represented as a phi on a dense subset of that Bargmann-Fock space.
So even for these densely defined Toeplitz operators, we still have that convolution representation in the QHA framework.
Exactly. This proposition is crucial.
Yeah.
Because it allows us to use all those QHA tools,
Okay.
like the Young's inequalities and the properties of that operator heat semigroup, to analyze these more general operators.
It's amazing how QHA seems to bring everything together for understanding these Toeplitz operators, whether they're bounded or densely defined.
To illustrate this connection, they give us example 4.3. Okay.
Which looks at a specific Toeplitz operator that has the heat kernel as its symbol.
What's so special about this example?
It's a concrete way to see how QHA can be used to analyze the boundedness of these densely defined Toeplitz operators.
Okay.
They show that the Toeplitz operator with the symbol key-deller is bounded
Okay.
if and only if the heat kernel parameter $2 meets a specific condition.
So it's like a test case,
Yeah.
showing that the QHA approach works in a specific scenario.
Exactly. It gives us a real example of those abstract ideas and paves the way for the more general stuff that's coming next.
It's getting exciting now. We've done all this groundwork.
I know.
Now it's time to see how they use QHA to actually tackle the Berger-Coburn theorem.
I know. I can't wait.
Let's turn to page 6.
All right. So on page 6, we finally get to the main event, the simplified proof of the Berger-Coburn theorem using this QHA approach.
This is what we've been waiting for. How does the proof actually work with QHA?
So they start by using that connection we talked about before.
Remember how they expressed the t-Berezin transform of an operator as that convolution of the operator with the operator heat semigroup?
Right. Tilde ETLT.
Exactly. Now they take that representation and combine it with Young's inequalities for QHA convolution to analyze the boundedness of that Toeplitz operator.
Okay. And Young's inequalities give us those bounds on the norms.
Right. They relate the size of the convoluted thing to the size of the original pieces.
Gotcha.
So by applying these inequalities to that convolution representation of the t-Berezin transform, they're able to establish the core of the Berger-Coburn theorem.
Okay.
They show that if that t-Berezin transform of the symbol us, which we denote as t-Berez, is bounded for some less than 1/2, then the Toeplitz operator t-Berez is also bounded.
Right.
And conversely, if t-Berez is bounded, then t-Berez is bounded for 2 greater than 1/2.
That's pretty amazing. So by using QHA and those inequalities, they've really streamlined the proof and avoided all those complicated pseudo-differential operator calculations.
Exactly. The beauty of this proof is that it's so elegant and clear.
Right.
QHA really helps us see the underlying structure of the Berger-Coburn theorem in a way that the traditional methods, which often rely on all these intricate calculations, just kind of obscure.
It's like they've cleared a path through a dense forest so we can see the destination without getting lost.
Yeah, a perfect analogy. And then on page 7, they start talking about Schatten classes, which are these special classes of operators.
Right, they're categorized by their size
Yeah,
in a specific mathematical way.
exactly. And what they do is establish this quantitative relationship between the Schatten class membership of a Toeplitz operator and the properties of its heat flow.
So the heat flow that Toeplitz transform not only tells us if the operator is bounded, but it also gives us information about its membership in these Schatten classes.
Precisely. In theorem 5.3, they prove that if the L-Buller norm of that Toeplitz transform of the symbol, which is tilde TP, decays fast enough as TIL approaches 0, then the Toeplitz operator Toeplitz belongs to a specific Schatten class.
Interesting. So the rate at which the heat flow decays tells us how small the operator is in that Schatten sense.
Exactly. And what's really cool is that this actually answers an open question that was raised in some earlier research.
Really?
It provides a much more complete understanding of that connection between the heat flow and the properties of these Toeplitz operators.
That's awesome. It's like they've given us a brand new tool to measure these operators.
On page 8, they then focus on the compactness of densely defined Toeplitz operators.
Compactness. It's a key property for operators.
Absolutely. It's often crucial for proving all sorts of results in operator theory.
And they use the heat flow to figure out if a densely defined Toeplitz operator is compact.
Yes. In theorem 5.4, they prove that a densely defined Toeplitz operator 2 Doppler letter is compact if and only if the Toeplitz transform of its symbol, tilde call, vanishes at infinity for some tildes greater than 0.
So basically, the heat flow has to disappear as we move further away from the origin for the operator to be compact.
Exactly. It's like the operator's influence fades as we get further out in that complex space.
That's a beautiful way to think about it. And again, they highlight that their proof using QHA is much simpler than earlier ones that use pseudo-differential operator.
Yeah. QHA seems to be the key to understanding these operators on a deeper level.
For sure. So what happens on the following pages?
Well, pages 9 and 10 get into the nitty-gritty of proving those big theorems. We see how they use the QHA convolution, the operator heat semigroup, and those Young's inequalities.
It's amazing how they've connected all these different concepts to make this work.
I know, right? And then on page 11, they go back to that open question about the boundedness of the Toeplitz operator when the heat flow is at 2 equals 1/2.
And mystery we talked about earlier.
Yeah. And while they don't actually solve it, they do give us some great insights into why it's such a tough problem.
So it's still an open challenge for future research.
Exactly. They talk about how the current QHA approach isn't quite enough to solve it. But then on page 12, they give us some possible directions for future research. They suggest maybe looking at different versions of QHA or combining it with other techniques.
It's like they're leaving us with a little cliffhanger, inviting us to explore further.
Absolutely. The paper ends with a really nice summary of their findings, emphasizing how elegant and powerful this QHA approach is. They point out how much it simplifies our understanding and proofs of the Berger-Coburn theorem and those related results.
This deep dive has been incredible. We've explored this intricate world of Toeplitz operators.
We've learned about this awesome framework of quantum harmonic analysis.
And we've seen this super clear proof of the Berger-Coburn theorem.
It's been a great journey. What stood out to you the most about this paper?
I think the most remarkable thing is how they've brought together these seemingly different areas of math.
Yeah.
They've shown how quantum mechanics can help us understand operator theory, and that's given us this whole new perspective on a classic theorem.
Absolutely. It shows how connected math really is.
Right. Ideas from one area can unlock secrets in another.
Exactly.
And the fact that this QHA approach tackles that open question while also bringing up new ones makes it even more exciting.
For sure. It encourages us to keep researching and exploring operator theory with these powerful tools.
This is just the beginning of a fascinating journey into operator theory and quantum harmonic analysis. We encourage you to keep diving deep into these topics and see where they take you. Keep exploring, keep questioning, and until next time, keep those brains buzzing.